I'm Amelia. I was a student in this class in 2023. I was the head TA last year in 2024. I'm currently a PhD student, and today I'll be continuing our discussion of Bayesian networks. So briefly going over the agenda and some resources before we get started. We'll begin with a review, then we'll talk about parameter learning, and then structure learning. In this course, we're incrementally relaxing assumptions. So when we began working with Bayesian networks, we assumed that both the parameters and the structure were known. Then we relaxed the assumption that parameters are known and learn them from data. We relaxed the assumption that structure is known and learn that from data. And ultimately, we can learn everything from the data. So some resources that may be helpful. There's the textbook, Algorithms for Decision Making, and this will most closely follow the lecture. I'll also be writing headings that have the sections of the book that correspond to what I'm talking about. If you want to go more in depth to Bayesian networks or other graphical models, I highly recommend the Kohler and Friedman textbook. Jack's course notes, which you can find at this URL at jamilka.com, and that will also be shared on Ed later, are a great summary of the most salient topics from each of the lectures. And finally, for Project 1 in particular, which you'll have all the information you need for by the end of today's lecture, highly recommend checking out the videos on the course website on the Project 1 page for tips on where to get started. So a brief review of Bayesian networks. Why are they something that we want to study? The power of a Bayesian network is that it compactly represents a joint distribution by encoding conditional independence assumptions. And I'll give you an example so we can take a closer look at what that means. So here we have three binary variables, x1, x2, and x3. And these are going to represent whether or not it's raining, whether or not I'm wearing rain boots, and whether or not I'm carrying an umbrella. When we say a Bayesian network encodes conditional independence assumptions, we'll want to recall the definition of conditional independence. So we say that x is conditionally independent from y given z if and only if the probability of x and y given z is equal to the probability of x given z times the probability of y given z. In other words, the way we can think about this is that once I know z, knowing x doesn't give me any more information about y. And we can look at how that might be encoded in this network. So this is the way that we could connect the nodes such that rain boots and umbrella are conditionally independent given that it's raining. And this makes sense. Once I know that it's raining, knowing that I'm carrying an umbrella probably doesn't give me any more information about whether I'm wearing rain boots. However, if I had no information as to whether or not it was raining, and I wanted to know if I'm wearing rain boots, whether or not I'm carrying an umbrella would be a helpful piece of information. Now I'm going to give you a bit of notation that we'll be using throughout the lecture, and then we'll get into the new material. So first, we have x from 1 to n, and these are our discrete random variables in the Bayesian network. So here, in this example, n would be 3. We have 3 random variables. R sub I is the number of possible instantiations of node x sub I. And an instantiation is just a value that node can take. So since these are binary variables, each of them would have 2 possible instantiations. Then we have q sub I, and that's going to be the number of parental instantiations of x sub I. And I'll give you another example to show what that means and how we would find that number. So let's say now we have this network. We have x4, x5, and x6. And x4 and x5 are the parents of x6. Neither x4 nor x5 has any parents, and so when that is true, we say that qi is 1. So we would say q4 equals q5 equals 1. And then if we do have parents, the qi value is going to be the product of the ri's of those parents. So in this case, q6 equals r4 times r5. We're still working with binary variables, so this will be 4. We have one final piece of notation, and that's going to be pi ij. And this is the jth parental instantiation of the parents of xi, or just of xi. The jth parental instantiation of xi. So if we look at what the different parental instantiations here could be, we have x4 and x5, and we're going to say they could both be 1. 1 could be 1 and 1 could be 2, and then both could be 2. So there are 4 of these, so if we had pi 6, 3, that's going to be this row right here. This is the third parental instantiation of node 6. Yes?
Does it actually matter the order that you find table values for them? Because then if you swapped the way you wrote it out, it would be...
You just need to make sure that you're storing it in a consistent way. So as long as you can do that mapping the same way every time, there's no right or wrong ordering.
I see.
You want to repeat that question?
Oh, yes. And to repeat the question, it's which index we're using here for j and pi ij depends on how we've ordered the rows in this table. Is there a particular ordering we should use? And again, the answer is no. You just want to make sure that you're doing the mapping consistently so that you always get the same thing. But you can do that any way that makes the most sense to you. All right, so parameter learning. In the work that we've done so far, we assumed that the parameters of our network were known, and we've used that to do inference. And let's look again at this example that we have, and I'll talk about what the parameters mean. So we have raining, wearing boots, and carrying an umbrella. And for the purposes of this example, we're assuming the graph structure shown. We would say that our parameter theta ijk is the probability that xi equals k given pi ij. So they're going to end up being the summation from I equals 1 to n of Ri times Qi total parameters. So 1 per parental instantiation and node instantiation. And then of these, the summation from I equals 1 to n of Ri minus 1 times Qi will be independent parameters. Now, why are the parameters something that we want to learn? Let's take one example. So we're going to take theta 3, we're looking at node 3, with the second parental instantiation and the second node instantiation. So in this case, to be consistent with the notation in the book, I'm encoding true and false as 1 and 2 rather than 0 and 1. So in this case, we're saying this parameter represents the probability that I am carrying an umbrella given that it is raining. And what if that parameter were 0? We can see this probably wouldn't be a great model based on the intuition we have about the world. Similarly, I personally lose my umbrella fairly often, actually multiple times in this classroom. So having it be 1, also not a great fit to the data. How do we find parameters that are a good fit? We're going to talk about 2 different options. The first is maximum likelihood estimation. So as in previous courses, lectures, we are looking for theta hat, our best parameters that maximize the probability of our observed data given those parameters. And there's just one change that we're going to make to this for extending this to a Bayesian network. It's going to also be given our graph structure G, which we're assuming to be known. We need one more piece of notation before we solve this, and that's Mij, which is the number of times that x sub I equals k given parental instantiation j in our observed data. So we can write out the probability of our entire data set given parameters theta and a structure G with this product. It's going to be the product from I equals 1 to n, from j equals 1 to qi, the number of parental instantiations for node I, and then from k equals 1 to ri, the number of node instantiations, of theta ijk to the power mij. And I'm going to talk for a moment about where this comes from. So we're assuming that all of the samples in our data set are independent. Then if we want to find the probability of the data set as a whole, we can take the product of the probabilities of each of those samples. And as we've shown previously, we're using our parameters to represent the likelihood of a given node value with a parental instantiation. So if we observe x 1, 1, 1 2 times, we would have that theta value, theta 1, 1, 1, twice in our product. So this would be to the power 2, which is that count of how many times we observed it in the data. Basically, this gives us a slightly more compact way of saying to multiply the parameters representing the likelihood of each data point we've observed. If we take the derivative of this and find where that probability is maximum, we get our optimal parameters, theta hat ijk, are mij all over summation over k prime. That's just all the possible values that our node I could take on of mij k prime. So if we're using maximum likelihood estimation, these are our best parameters. But just looking at this formula, can anyone see any potential drawbacks of this approach? Yes.
So what do the I, J, and K indices that each represent?
Yes, great question. And this is one of the things that I found trickiest when I was learning the material. So throughout the lecture, we're going to be using indices with 3 positions. The first position will always be the node that we're referring to. So if we're looking at this graph and we had M1, or let's say M2, so we have a parent, then that would be talking about this node here. The second index is which parental instantiation. So if it's M21, this is the first instantiation. And since we just have one parent, that's going to be the parent taking on its first value. And then the third index refers to the value that the node is taking on. So M212 would be the first parental instantiation and second node instantiation of node X2. So in this case, where we're using a binary encoding, this would be the count of times that I've been wearing boots when it was not raining. With this being wearing boots, not raining, and then this is the node that we're talking about. Yes?
But the one for the parental instantiation is just the first parent and not necessarily because it's X1, right? So if there was like X5, X6, it would be 1 and 2.
You're saying if we had two parents, so if we had like X5.
Well, I mean, it seems ambiguous that it's the first parent, but also X1.
Oh, I see what you mean. Yeah, so because there's only one parent in this graph, the two possible parental instantiations, which is just Ri equals 2 for that node, would be 1 and 2 because it's binary. But let me see if I can think of an example where it would be a little less confusing. We can.
I guess if there's two parents, like X5, X6.
Yes.
Would you enumerate that 1 and 2?
Oh, I see what you mean. No, so if there are two parents, X5 and X6, and we have something like this, then when we look at all possible parental instantiations, we're looking at the product of values that they could take on, the Cartesian product. So if these are binary, we would have 1, 1, 1, 2, 2, 1, 2, 2. And as I mentioned earlier, the ordering you put them in that table doesn't matter. You just need to do it consistently. So then here, the first one would be this row where they're both 1. All right, great. So that's how we would get our parameters if we're using maximum likelihood estimation. Yes?
Can you just repeat one more time, like, what each number means?
Yes, for sure.
And also, like, go back so that I can see.
Yeah, so when you say what each number means, are you referring to these definitions here or on the other page?
No, yeah, the same question, the subscript, the IJQ.
Okay,
I think I got lost a little bit.
it's easy to get lost there. Let me write that out one more time. So M, I, J, K. What we have here is we have the ith node with the jth parental instantiation. And the kth node instantiation. So the indices are saying which node are we at, what are the values of its parents, and what is the value of that node. Yeah, no problem. I'm going to take one more question, then move on. Yes?
So an instantiation is just a set of values of the various.
Yeah, it's for the node itself, it's going to be a single value, and then for the parent or parents, it's a set of values. If there are no parents, we would just always denote that the same way. Move on. Yeah. All right. So, looking at this formula here with MIJK, this is coming from our observed data set. And one place where maximum likelihood estimation can be weaker is that there are some things that could happen in the world that we just haven't observed in our data set. So for example, let's say that I collected data over a week when it was raining, but it was a week when I had lost my umbrella. So we're going to have 0 counts for me having my umbrella when it's raining. And here we would find that the optimal way to parameterize that was to say there's a 0% chance that I'm carrying an umbrella given it's raining, which intuitively we know based on our priors is probably not a great model of the world. And so one other method we have available to us that addresses some of these limitations is Bayesian parameter learning. So unlike MLE, where we're finding a point estimate, theta hat is the argmax of the probability of our data given that theta. In Bayesian parameter learning, we instead find the likelihood of parameters theta given the data set. So we're actually inferring a distribution here. And then to find our best parameters, we would say that optimal parameters theta hat maximize the likelihood of those parameters given the data set. And we also refer to this as a maximum a posteriori, or map estimate. When we apply this to a Bayesian network, we would be looking at the likelihood of our parameters theta given some graph structure G that we still assume to be known. And here theta represents all parameters in our network. So that's just a compact way of writing that. And this probability is going to be the product from I equals 1 to n. So that's over all nodes. And from j equals 1 to qi. So over all parental instantiations of p of theta ij. And when I say theta ij, I am referring to this vector. So theta ij is theta ij1 to theta ijn. So for the ith node and the jth parental instantiation, we have one element in this vector for each instantiation the node can take on. And we are able to assume that this probability is taken from a Dirichlet distribution. So you'll recall from the previous lecture that these alphas in our Dirichlet distribution are pseudo-counts. And I'm actually going to briefly go over a few more things about Dirichlet distributions before we move on. Oh, yes. Yes. So the Dirichlet distribution generalizes the beta distribution to an arbitrary number of categories. It's parameterized by our alphas that are pseudo-counts. And when we observe new data, we just update the counts. So after observations, we would have these counts added in. And in our Dirichlet distribution, the likelihood of parameters, so for the simplicity of notation, I'm just going to write theta from 1 to n, given alpha from 1 to n, is equal to the Dirichlet of theta given alpha. And this is going to be proportional to the product over all n of our parameters theta to the power alpha minus 1. And I say proportional rather than equal to because we're missing a normalization constant that we need to make sure that these probabilities all sum to 1. And that's just using our gamma functions that you'll recall from the previous lecture. So that constant is going to look like this. We have gamma alpha 0 over the product from I equals 1 to n of gamma of alpha I. And then just that normalizing constant times the products we initially had. I saw a question over here.
Yeah, I was just curious what sort of notation for the last subscript of your summation m sub ij r I and alpha sub ij r I. What is that saying exactly?
Okay. So this would be looking at some node xi and parental instantiation j. And then we have one parameter theta for each instantiation that the node can take on, and there are r sub I possible instantiations for node I.
Oh, so it's m I j r sub I.
Yeah, that's r sub I.
Oh, okay.
Yes. Yes, one more question.
Is the alpha, is that the priors?
Sorry, would you please repeat that?
Is the alpha, is that priors?
Yes, those are priors, so those would be pseudocounts. And as previously, the higher the pseudocounts are, the more confident we are. All right. So given the Stirchley distribution, when we take the likelihood of our parameters given our graph, we're looking at the likelihood of theta ij given alpha ij, our pseudocounts, so that would be the prior, and mij, which is our data set, and we're just counting up how often we've observed things in the data. And we're saying that this is Stirchley distribution. So, one parameter for each r sub I, or value that the node can take on. And there are sub I of those for node I. I'm going to give you an example of how we actually compute these parameters because it's a bit more complicated than what we were looking at for the beta distribution. So suppose that, again, we're working with binary variables and we have this graph structure. We have x3 and x4 that are parents of x5. Now, the number of parameters that we have for each node depends on the number of node instantiations and parent instantiations, and we can store the parameters in a matrix. So first, we're going to do the matrix for x3, and this is going to have Q3 rows, so the number of parental instantiations. Since it has 0 parents, we say that there's 1 parental instantiation, and then it's going to have R3 columns. So the number of node instantiations, there are 2 values the node can take on. And we're going to have the same shape of matrix to hold the parameters for x4. So Q4, we have 1 parental instantiation since we have 0 parents. And R4, we have 2 possible node instantiations since it's a binary variable. And then the one where things are a little bit more complicated is x5. So now, since we have 2 binary parents, how many parental instantiations would we have? 4. Yeah, exactly. So we're just taking R3 times R4 to be Q5. So we're going to have 4 rows in this matrix, and then again, the node itself is binary, so R5 is 2. Yes?
Can you write down like what each one is? Can you write down like R3 equals? This is R3 equal 1?
Oh, yes, sure. So R3 is 2,
Okay.
R4 is 2, and R5 is 2. Q3 is 1, so is Q4, since neither of them has any parents, and Q5 is 4, since we have 2 binary parents. If we assume a uniform prior, we can populate all of these matrices with 1s. And then we're going to look at what happens if we observe some new data. So how do we update our pseudo counts with our observed counts? Let's say we make the observations in this table. I'm going to begin with x3 and x4 since those are easier. So for x3 here, we have one observation of it taking on value 1. And again, you can order the columns and rows in your matrices any way that makes sense to you. You just want to be consistent. But I'm going to order them so that the first column corresponds to value 1 and the second to instantiation of the node 2. So we have x3 being 1, so we're going to increment the first column and first row by 1. And we'll apply that same thing to x4, except we've observed it being 2, so we're incrementing the second column. Where things get a little bit more complicated is with what we're going to do with x5. We've observed x5 to be 1, so we know that we're over here in this first column. And then again, you can choose to order the rows by parental instantiation, however makes sense to you, but I'll show you what I'm doing here. And so when we look at our table, we have parental instantiation 1, 2. So that's putting us in our second row and the first column. So we'll increment that count by 1. We can do, yes?
Can you just explain more intuitively like what you were doing there and what you're doing now?
Do you mean what I'm doing in the matrices?
Yeah, and just the formula you had before that.
This formula.
What?
Right here?
Yeah.
Okay, sure. So our theta ij parameters represent a distribution over outcomes. I think it's a little bit more intuitive for me to think of it as like a dice roll. So with a dice roll, let's say that we just have one variable and it represents a die. There's 6 faces on the die, so we're going to have 6 instantiations it could take on. So this will be 1, 2, 3, 4, 5, and 6. Maybe we think that it's probably a fair die, so we're going to begin with our theta parameters representing a uniform distribution. So these parameters will just all be 1/6. And then based on our observations, we want to infer how likely these parameters are. And the motivation for doing that is then in the future, we can say, is this theta a good model for data we might observe later on? Like maybe if you're betting on rolls of this dice, you want a theta that matches it really well. So we can begin with our Dirichlet distribution parameterized uniformly. So let's say our alphas are all going to be 2. And this represents a weak confidence that the die is fair. Then we observe some data, and so if we just took the Dirichlet likelihood of theta based on these, it would probably be reasonably high, not like 99% because we're not strongly confident, but reasonably high. And then let's say I roll the die 100 times and I only get 1. So I'm going to increment this pseudo count. We have alpha 1 plus m1, our observations. And now our Dirichlet distribution parameters are very different. So if we once again take the likelihood of this theta using those parameters, now we're going to see it's much, much less likely that theta accurately represents the data. All right. Yeah, no problem. Yes.
Right, so when we have 2 to 2, that's when you have, like, we just roll the dice once, right?
2 to 2 was our prior, so we hadn't rolled the dice at all, and we can set that prior any way we want to based on what we believe to be true and how confident we are. So if we believe that maybe we're a little bit more likely to get 1 than we are anything else, we might have a prior alpha that looks like this. Maybe we have like 5 and then everything else is 2.
And if we roll 1, if we roll 1,
Yes.
and the first, like, you have 1,
Yes.
then we just add 1 to that.
Exactly. So now we would have 3, 2, 2, 2, 2.
Okay.
And so we can see that here, even though the only thing we've actually observed in our data is rolling a 1, it's still going to be a reasonably good fit to the theta we have that's a uniform distribution.
Yes.
So, in this case, a uniform prior would just be going across the board for all of our preconceived alphas.
Great question. Okay, this is one of the coolest things I think about the Dirichlet and beta distributions is that we can express not only the shape of distribution we're expecting, but also confidence. So we could have priors representing a uniform distribution with any confidence level. Let's say that we're starting off with this distribution where our confidence is weak. And we roll a 1 twice, so now we have a 4 here. That's going to have a much bigger impact than if we had had a strong prior where they were all 100 and we rolled twice. So you can have many uniform distributions with the magnitude of the prior parameters indicating confidence. All right. So that's the Dirichlet distribution, and we're going to see it again momentarily as we get into structural learning. So in order to learn structures from our data, we need a way to score them. We want some reasonable objective measure that allows us to say a certain graph structure is a better fit to the data than another. Let's look at our rain example again. So the current structure that I have, these nodes are totally unconnected. And what this implies is that they're fully independent from each other. There's no probabilistic relationship between them. Based on our priors about rain and umbrellas and rain boots, we know that's probably not a great model. And we want to be able to score it so that something like this would be better if it's supported by our data. What we're looking for, in other words, is the probability of a graph given our observed data set. From Bayes' rule, we can see that this will be proportional to the probability of the graph times the probability of data given the graph. And using the law of total probability, we can see that this is equal to the integral over all possible thetas of, that should be on the outside. That's equal to the probability of the graph times the integral over theta of probability of the data and theta given the graph d theta. So I'm just writing out how we're doing each step. Bayes' rule, law of total probability, and then finally we're applying the chain rule. And we're going to get probability of the graph times the integral over theta of the probability of d, our data set given theta, and our graph structure, times the likelihood of theta given our graph structure, d theta. All right. So we're following the same assumptions we did previously about this following a Dirichlet distribution. And we're able to write probability of the graph given the data is the probability of G times this product, I equals 1 to n, so that's over nodes, then j equals 1 to qi, over parental instantiations for node I, gamma function of alpha ij0, all over the gamma function of alpha ij0 plus m ij0. And these are just going to be summations over all alphas for I and j, and over all m's for I and j. Then this will be times the product from k equals 1 to ri of gamma alpha ijk plus m ijk, all over gamma of alpha ijk. Now, why are we able to write that? The answer is a 2-page derivation that you can find in the references of the textbook and that you don't need to know. But if you're curious, it is out there. And there's, yes?
Sorry, in your exam, said about something you wrote about.
Yeah, so I was just going to say there's only one more step we need to take in order to put this in the form that you'll be using for project 1. But yeah, don't worry about the derivation. Yes?
Okay, it's a very simple question, but Bayes' rule, like, there's also a term with, like, the probability of D, right?
Yes.
But does that go to 1 where you can still have the data assumed? Like,
No, it doesn't go to 1. That's why we're saying proportional instead of equals to.
oh, okay.
Yeah.
So it would be like divide with some division.
Yeah, so if we were just writing this out with Bayes' rule, we would have this. And the reason that we're okay with using something proportional to the quantity is that we just care about maximizing it. So if we know that the left and right-hand sides are proportional, even if they're not equal, maximizing what's on the right-hand side will still maximize the left-hand side. So we're just dropping that term for the optimization that we're doing. But you are right that that would be in Bayes' rule. All right. So the last step we're taking is that for stability, we're applying the log trick. As you can see here, we're starting to multiply out a lot of very small probabilities. And instead of multiplying them, we are going to take the log so that we can be adding them. So we have the log probability of our graph, and then this big summation over the logs of those ratios of gamma functions that we had previously. Oops. So gamma alpha ij0 all over gamma of alpha ij0 plus m ij0. And a tip for you on the project is I highly recommend you start from implementing the score. We give you an example that allows you to check that your score implementation is correct, and that is definitely the best place to begin before you move on to searching over graph structures to maximize the score. Oops, and we're getting a little phosphor space over here, but it's the same ratio, just inside of a summation now. A couple more notes on this as it applies to your project. So often we have no idea what graph structure is best. So in that case, we can have P of G drop out and we don't worry about it. Sometimes there are cases when we know a particular edge has to be in the graph or can never be in the graph. So in those cases, we could say, okay, if we ever have a graph with this edge that has probability 0, and the probability of all other graphs is going to be uniform. Another way that you can implement that practically is you can enforce the constraint by saying just never add the prohibited edge, or always add and keep the required one. So you won't need to compute P of G in the assignment. That's how you would handle your beliefs over graph likelihood. Yes?
I see an open parenthesis after the double summation.
Yes. That closes right over there. Good catch. Definitely want to be careful of that for the assignment. All right.
Say something about the log function.
Oh, there's something that I'd like to say about the log gamma function.
So computing the gamma function, remember it's a factorial. You don't want to be computing those factorials because the factorials go super fast. But computing the log gamma, that we can do, and it's a built-in function for everything.
Yes, including Julia. So use that for your project, please. All right. Now, something cool that happens when we optimize for this score is that it balances model complexity and the amount of data. And I'm going to do a drawing of figure 5.3 that you can find in the book. But basically, we are looking at, on the y-axis, Bayesian score, so this quantity here, relative to the true network structure. And so up here we have 0. If the Bayesian score relative to the true network is 0, that means that the scores are the same. And then things are getting negative, so down here is how much worse we are than the score of the true structure. And then along the y-axis, we have the number of samples in our data set. So 0, 5,000, 10,000, 15, and 20. And I'm going to use pink to represent a completely unconnected graph. And so we would see that this relative score curve looks like this. So at the beginning, when we don't have much data, we actually get a higher score for a completely unconnected graph than we do for the true graph. And as the amount of data increases, we're penalized more and more heavily for not modeling any connections. And let me label that quickly. This is completely unconnected. And then we'll also look at completely connected. So if our graph is completely connected, at the beginning we're doing worse. We're being penalized for having more complexity than we can model based on the data. And then things kind of plateau. So ultimately, if we have enough data, the completely connected graph outperforms the completely unconnected graph. Although, of course, what we want to find is something as close to the true structure as possible. So neither of these is optimal. Yes, in front row?
Why does the completely unconnected go above 0?
Yeah, great question. So because of how the Bayesian score works, if we don't have very much data, meaning that there are many parameters where we don't have a count, a lot of our MIJKs are 0, that it doesn't perform well. So in a small data set, we might not have observed all of the relationships modeled by the true structure. So we're doing a little bit better by modeling things as totally unconnected with a certain amount of data, and then that drops back down once we have more data. Yes. Yes.
I just wanted to ask about the structure of the network itself.
Sure.
Went over the conditional display.
Yes.
Sort of like the likelihood. I just wondering what maps to the prior distribution and maps the likelihood in the network.
So when you say the prior distribution, you mean the prior over all graphs?
Yes.
Okay. That would be this P of G term that's dropping out. So typically right here. And it's not dropping out mathematically, but if you don't have a prior, you can just disregard that when you're computing the score. an example that hopefully isn't too much of a hint of another way to deal with it is, like I said, you can enforce some edges. So for the project, the first small graph is about the score of wine based on a number of factors. And my parents are winemakers, so I asked, are there any things that you are super confident should be connected? And then I would say have those be connected every time. So that's a practical way of implementing a prior rather than trying to assign some probability to every graph structure. And actually the space of graph structures is so large that we can never search all of them for any reasonable number of variables. Yes?
So this graph at the bottom, we aren't updating the graph structure as we get new data.
No, we're not updating it at all. So we're taking two models that probably are not an amazing fit for our data, totally connected, totally unconnected, and then we're looking at how they score as we increase data. So the important takeaway here is that using the scoring metric, it penalizes you for having a lot of complexity if you have a small amount of data, and encourages only modeling complexity that your data can justify. So basically, this gives us more empirical evidence that we're not going to do some kind of weird reward hack and say, never connect anything or connect as many things as possible.
Okay.
Yeah.
When you say completely connected, you mean just like every node has to have at least one arrow just above the node. But it could mean like it has like any number of connections.
I believe that would be every node is connected to every other node with the edges directed such that no cycles are created.
Okay.
Yeah, so an example of that would be if we have x1, x2, and x3, we could have something like this. So there's no cycles, but every node has an edge between it and every other node.
So there's no cycle because there's no loop where all the arrows point in the same direction.
Exactly. Yeah, I mean, this is not the most mathematical way of doing it, but when it comes to cycles, I'll just start at a node and trace its edges and see if I can get back to it or not.
Okay.
All right. So this question of cycles is important because now that we have a scoring function we can apply to our graphs, we can talk about how to find the best ones, and this is structure learning. So I'm going to give you two different techniques, both of which would be suitable for project 1. And the first one we're going to talk about is the K2 algorithm. So this is polynomial time, and it is not guaranteed to find a global optimum. And I'll show you how it works. So in K2, we begin with a completely unconnected graph. So no edges. So maybe we have something that looks like this. And then in some order, in this case I'll choose a very simple order. We're going to iterate over the nodes. So I'm choosing x1, x2, and then x3. As we iterate over the nodes, we greedily add parents to maximally increase the score. So what that means is that we're keeping track of our best score so far. We're starting off probably not an amazing best score so far since we're fully unconnected. And then in our order, we'll try to add parents. And if the score that we get when we add that parent is greater than our best so far, then we'll keep that edge in the graph. So starting at x1, there are no nodes before it, so we can't add any parents to it, and K2 enforces this order constraint. Then at x2, x1 is before it, so we'll look at that as a potential parent. And if the score increases, we'll add that edge from x1 to x2. And then at x3, we will look at x1 first as a potential parent and see whether adding that edge is going to improve upon our best score. If so, we add it. And then the same logic at x2. If adding that edge to x3 would improve the score, we add it to the graph. And so actually here in this image, I've added every edge that I possibly can according to the constraints of K2. And you'll see that because we've enforced this ordering, we're never going to create a cycle. We can only add edges in one direction and we'll never go backward. So that's how K2 handles the issue of cycles. I saw a question over here.
Yeah, I guess you already asked the question the other bit, but I assume that there's the issue of approaching a local maximum instead of the absolute with this.
Yes, exactly. So one way of dealing that, as you can see here, we were limited in which edges we're able to add by the initial ordering that we chose. Something you could do is you could try multiple initial orderings, just randomize a bunch, and then take the structure that was best out of all those orderings. But yeah, this is prone to that, so you need to artificially expand the search space. Another thing you'll want to be attentive to for the project is enforcing a maximum number of parents. So this is a very small number, but the parameters that we need grows exponentially with number of parents. And for the sake of your compute, highly recommend setting a limit. You can start with something super low, like only 2 parents possible, and then you can increase that as your resources allow. Yes?
So in general, with this algorithm, you assume that whatever node you start with, iteration, does not have any parents?
Yes.
So like if you change the order to start with x2, then you would assume x2 parents.
Exactly.
Okay.
Yeah, so we're totally limited by what that ordering is. And if you have a data set where, I don't know, some node, like say x1 should have many parents, if you randomly get an ordering where x1 is first, then you're out of luck for all of those potential structures. Yes?
Does this find the maximum for that ordering? Like, is this strategy finding the optimum given that parental assumptions you're making, or no?
Given all the assumptions that you're making, does this find the optimal one? I don't think so because we're adding greedily, but no, this does not. All right. So we have another option for how to deal with this, and that is local search. Local search is also prone to local optima, but after I describe the algorithm, I'll tell you about a few ways that we can deal with this because there's some interesting options. All right, so in local search, unlike K2, we begin with some initial graph structure, and you could begin with things fully unconnected, but you don't have to, whereas with K2, you do have to begin with no edges. Although actually, as I'm saying that, for K2, if you had an edge that you wanted to enforce, you could begin with that edge. You just want to make sure that in your ordering, the edge isn't going backwards so that you're not introducing a cycle. Okay, so for local search, we're beginning with an initial graph. And for the sake of this example, I'm going to have it look something like this. And the reason that we call this local search is that we're going to be looking at all of the graphs in our current graph's neighborhood. So I'm going to define neighborhood. So the neighborhood of a graph is the set of all graphs that are a single basic graph operation away from the current graph. There are 3 basic graph operations. First, we can add an edge. So this would give us, there are a number of edges that we could add here so long as we're not introducing a cycle. But one example would be we could add an edge from x2 to x3. The next basic graph operation is we could remove an edge. So in this case, since we only had one edge to begin with, that would result in a fully unconnected graph. And then finally, we can reverse the direction of an edge. So we only have one edge to choose from in our initial graph, and we're going to flip it so that now x2 has an edge into x1. And as I mentioned at the beginning, there's more than just one edge that we could add, so our neighborhood will be a bit larger than this, but it's just everything that's one basic graph operation away. So we start off with some initial graph. We have all of the graphs in its neighborhood, and then in local search, what we're going to do is we'll score all neighbors so long as they don't introduce cycles, and then we move to the highest scoring neighbor. So now the highest scoring neighbor is our current graph. And we just keep on repeating this process until we reach a point where for the current graph, there's no neighbor whose score is better than that. So repeat until current graph has no higher scoring neighbors. So as we saw with the previous example for K2, this is also very prone to local optima. And we have some interesting ways that we can get out of that. So first, we have randomized restarts. And all of these will be in the book in detail. So don't feel like you have to remember them all now. But for randomized restarts, we just take one of the graphs that wasn't selected, so a neighbor of one of the graphs we visited, and then you restart the search from there. In addition to randomized restarts, we have simulated annealing. This is inspired by metallurgy, and so in simulated annealing, we choose a neighbor with lower fitness or a lower score than the best neighbor some percentage of the time. And then we set this parameter percentage to decrease as we proceed in our search. So maybe we start off choosing not the fittest neighbor 50% of the time, and then that declines gradually. Finally, for examples here, but not for things that you could choose, we have genetic algorithms. So genetic algorithms are biologically inspired, and they begin from a population of individuals. So in this case, individuals are going to be different graph structures. We encode this population of individuals as a binary matrix. So where DNA has A, T, C, and G, this matrix is going to have 0 and 1. And we're starting with a totally random population. For each of the graphs in our initial population, we're scoring their fitness using the Bayesian score. And then to produce the next generation, we select two parents randomly, but with likelihood weighted by their fitness. So the higher Bayesian score, the more likely that structure is to reproduce. We recombine them, taking half of the DNA, or 0s and 1s from each, and we add some mutations. So we flip some of the bits that we get doing that. And then we continue reproducing our graph structures until some stopping criteria is met. So that could be based on time, which is probably best for managing your constraints or score or any other criteria. Is there a typical one?
Just until you run out of time.
Until you run out of time would be the typical one. So that's another way that you can address this local optima problem. I see a couple questions. Yes?
How do you enforce the basic graph in that case?
So when you're reproducing, you would just have to check that a cycle wasn't created, and if it was, you can sample 50% from each again, or resample in other ways. Yes?
So like in this context, like how do you read two graphs together to make a new?
Great question. So let's say that we have our initial matrix, and I'm going to have these be really simple. If we have 1, 0, 1, 0. And suppose that we're reproducing.
It needs to be a square.
Ah, yes. And this is a square matrix. Yes. If it represents connectivity, then we'd have one matrix per graph structure, right? Okay. So we're just going to take two possible parents. And for the sake of time, the second parent is going to be pretty much entirely zeros. All right. So then if we were to reproduce these two matrices with each other, we would be taking 50% randomly of the positions in one parent and 50% in the other. To make it a little bit easier for myself, I'm not randomly going to say that we're taking the first two rows of the first matrix and the last two of the second. And then that would produce a child that looks like this. And you would imagine that you can sample 50% of the different matrices in a number of ways, but that's just how I did it. And you can keep sampling until you have something with no cycles. Yes?
So in this matrix, is it basically each argument in the matrix represents like the connection or lack thereof of like the I, like you go like 1 to n on the rows, 1 to n across the columns?
Yeah, so this is just one way of encoding them, but here we could assign the nodes in this way. And so then if we have, let's take this one here, this means that there's an edge going from x2 to x1. And you can set the direction any way you want, just make sure that you're being self-consistent.
So does that mean by default they all have to be identity matrices? Because each node is connected to itself, like x1 and x1, x2, x2.
I think actually by default nodes should not be connected to themselves because technically that would be a cycle.
Oh, okay.
Yeah.
Okay.
Yes.
And just add to that, you can't have a node like x1, x2, x2 to x1. You cannot have x be a cyclic indicator.
Yes, you can't have that. Yes.
Is there a formula for calculating how big is the neighborhood? So how many graphs are there in the neighborhood?
Oh, good question. I'm not aware of a closed form equation for that. Do you know of one?
So it depends upon your graph operations.
Yeah.
You can add an edge, delete an edge, or flip an edge.
Yeah, and so for deleting or flipping, that's going to be based on the number of edges that you currently have. For deleting, you can always delete an edge because that will never introduce a cycle. For flipping, you have to check that it won't introduce a cycle. And then for adding, similarly, you have to make that check. But in practice, you would just iterate through and say, okay, out of all the edges that I don't have, if I add it and it doesn't create a cycle, what's the score? And then you would keep track of the best structure and the best score.
I would say asymptotically it's exponential in the number of variables.
Yes. Okay. Yes.
So technically in that matrix we have zeros in the diagonal, right?
Yes, we would. Yes.
And so more generally, like if this is the way you define your like node structure or graph structure, one way to like algorithmically check for cycles would just be to check that the element directly diagonal from any given element should not be equal to it, like on the graph.
That would be a way to check for simple cycles, but we can have more complex ones. Like we could say we have we could have a cycle that looks like this. right? I believe that we provide you code that checks for cycles, so don't worry too much about how to implement that. And an additional note on implementation is that just to pass all of the tests on the project, you don't need any of these modifications to local search. These would be more relevant if you're looking at optimal leaderboard placement. All right, cool. So we just have one thing left to talk about, and that is Markov equivalence. So we say that two graphs are Markov equivalent if they encode the same conditional independence assumptions. So encoding same conditional independence assumptions. And that sounds pretty complicated, but actually we just need to check for two things. First, we need to check that they have the same undirected edges. So I'll give you a couple of structures to illustrate this. Let's say we have x1, x2, and x3. So these do have the same undirected edges, right? Because we have x1, x3, x2, x3 in both. And then they also need to have the same immoral V structures. So you'll recall a V structure from previous lectures. This would be an example of one. And when I say that a V structure is immoral, what I mean, and this was not my definition, is that the parents are unconnected. So if we wanted to make this a moral V structure, we could do that, or we could do that. But as it stands in the example, this would be an immoral V structure. And so because of the second criteria, we would say that these two graphs are not Markov equivalent, since in this one, we have an immoral V structure here, and here we actually have no immoral V structures. So those are not Markov equivalent graphs. Yes?
Same count, or is it the exact same V structure?
Exact same V structure. Yeah, so let me draw out an example. All right, so okay, it's a little bit hard to think of an example, actually. I'm realizing how many V structures you end up creating. Maybe I'll just show you why this is tricky. All right, so we have graphs like this, and we can say what connects there. Actually, I think this works. We'll talk through it together. This will be a good example. So definitely have the same undirected edges. And then when we're looking at immoral V structures, we have this one here in both of the graphs. And here we have a chain, and here we have, is that a fork? Is that what you call that? A fork. So they have the same edges and the same immoral V structures, so we would say that those two graphs are Markov equivalent. The reason that we care about Markov equivalence is that the space of Markov, like sets of Markov equivalence, is much smaller than the space of all graphs. So one option is to search those Markov equivalence groups rather than searching the space of all graphs, and that's computationally much easier. And we think it's safe enough to do, given that they're encoding the same conditional independence assumptions. Although, as a note, two graphs in the same Markov equivalence group can have different scores, unless can have different scores within group, unless and this is a kappa. It's clear in the book, but that's not a k, it's a kappa. Unless we have kappa, which is the sum over j, sum over k of our alphas in the prior, alpha ijk is constant for all I. And that's I would say that's a pretty minor note, but just worth pointing out, Markov equivalent doesn't mean the same score, but we're assuming that it's close enough given it encodes the same independence assumptions that we can search over those groups rather than over all graphs. I saw a question. Yes?
So if they have the same moral structure or not Markov?
No, they are. So Markov equivalent if and only if these two hold.
So by saying the moral structure can just mean they're matching in their morality?
Oh.
Either both immoral or both moral?
So if there is, if we're looking at two graphs, A and B, if there is an immoral V structure in A, then that immoral V structure must also be in B in order for A and B to be Markov equivalent. And similarly, if there's an immoral V structure in B, that immoral V structure must also be in A. So the set of immoral V structures in each graph has to be the same for them to be Markov equivalent.
They have the same moral structure.
Oh, if they have the same moral ones? If the moral V structures are different, then we don't care. So let's look at another example. Let's say okay, so they have the same edges. And then if we connect the parents in different ways, we don't even need to look at, so we can connect the parents in different ways, and that would be fine. So for moral V structures, they can be different, but for immoral, they have to be identical. And so if we connected the parents in one and not the other, then they would not be Markov equivalent, because here we have an immoral V structure that we don't have in the other graph. No problem. Yes?
Just a quick question on the Bayesian score. When you derive that, is that from using like the math definition or the MLE?
That's from the map definition using the Dirson distribution.
Yes.
So you mentioned that we should search like in Markov equivalent graphs because they're like similar in some way, but I feel like that's a bit counterintuitive. I would have thought we want to like search over graphs with like different conditional independence assumptions.
Oh, yes, sorry, that's what I meant. So the question is, I said we can search over Markov equivalence classes because they encode the same conditional independence assumptions. So we would have our search space be all of the distinct classes rather than the distinct graphs. So we would say we actually don't need to look at two graphs between within one Markov equivalence group because they're encoding the same conditional independence assumptions. I think it would be a bit difficult to implement searching over equivalence classes, although you're definitely encouraged to try that, but I didn't for the purposes of the project, and it is sufficient, and there's plenty of optimizing to do in the graph space. Keeping an eye on time, I think we can do just one more question. Yes?
Is the kappa condition on like two different graphs have to have the same sum, or is it like for all I, or is it just like for each individual I there's a match?
Yes, so this is for graphs within the group, and I'm fairly sure that this could be accomplished by having the alphas be 1 because they'll all have the same edges. Oh, actually, they wouldn't necessarily have the same number of parents. Yeah, you need the sum to be constant within the group.
The book gives some examples.
Yes, the book gives some examples. All right, I think we're at time, and if there are more questions, we're happy to help at office hours. Thank you all so much.